Hi guys, this is Stoichiometry102 for general chemistry, and our topic today is gases at STP with stoichiometry and the concept of a percent yield. Your homework is, excuse me, the stoichiometry #2 worksheet, and we're just going to start off with an early basic statement that I'm not going to use green, I'm going to use purple. There are 3 states of matter that we that we study at this level of chemistry. One is a solid, the next is a liquid, and last is a gas. So if we were going to compare that to something that we're familiar with, this would be like ice, if we're talking about water, and a liquid would be drinking water. And then the common name for water vapor is steam. So water as a solid is ice, water as a liquid is just drinking water, and water as a gas is also known as steam. And so let's see, what else do I want to say? What we're interested in today are gases and how they are. And we want to make this general statement, or this specific statement, that gases at standard, I'm going to put that in quotation marks, temperature and pressure gases at standard temperature and pressure. So a standard temperature is 0 degrees Celsius, and pressure is 1 atmosphere of pressure, which is the pressure that we live under, basically at sea level. And gases at standard temperature and pressure have a specific volume, and that is that 1 mole of any gas at STP, standard temperature and pressure, has a volume of 22.4 liters. So I'll put a box around that, and we can write an equivalence. So we could say 1 mole of any gas at STP is 22.4 liters, or we could flip that over and say 22.4 liters of gas at STP is 1 mole. Okay, so this is what we're interested in, these 2 equivalents. And what we're going to do is connect this to our stoichiometry map. So we're going to connect to stoichiometry. And everything that I put in black in this next little part here, you've seen before, and then I'm going to add something to it. So what we're going to do is look at the stoichiometry map, and we want to remember that at its heart, every stoichiometry calculation is a moles to moles. So we'd have moles of known, this is whatever substance you're given information about, to moles of unknown. And we translate between the 2 of them using a mole ratio. And if you need a refresher on what a mole ratio is, those are the coefficients from the balanced equation, and it is the unknown over the known coefficients. Okay, and then the other thing we also talked about is if we're given grams, then we have to convert to moles. And so we use 1 mole over the molar mass of the known substance. If we're asked to answer in grams, then we finish with a molar mass on top and 1 mole on the bottom. So what we see here is 3-step questions if we're asked to go from grams to grams. So that's all the stuff you've seen before. So again, this is the stoichiometry map. Okay, so what I'm going to add in here, I'm going to use pink because I'm feeling pink, is what if we are given liters of gas at STP. So instead of being given grams, we're given liters of gas at STP. And so we can get to the moles known if we use this equivalence. So we can do 1 mole of any gas at STP is 22.4 liters. And additionally, if we're asked to answer in liters of gas at STP, we can do 1 mole on the bottom and 22.4 liters on top. Okay, now, if you're asked to start with liters and go to grams, you can do that. So you just start here and go this direction. You can go this direction. You could also go here, but you can see the 22.4 liters would cancel out. So it would just be like a moles to moles calculation if you were asked to start in liters and answer in liters. Okay, so we're going to do a quick calculation example. Example number 1. That green is super hard to see. We're going to use this reaction, C3H8 plus O2 makes CO2 plus H2O. And our balancing this, this is 1, 5, 3, 4. And we're asked if 10 liters of O2 react as above. At STP, we want to know how many grams of CO2 could be made. Okay, so let's identify where we're starting and where we're going. We have 10 liters of O2 at STP, and we're asked for grams. So we're starting here at liters at STP, and we're going up here to grams. So we're gonna go hop, hop, hop. Pretty easy. So we'll start here with this is our answer, this is our question. We'll have 10 liters of O2, and we're gonna use this equivalence because that equivalence is legitimate for any gas. So 1 mole of O2 at STP is 22.4 liters. And then we would have our mole ratio, and on the bottom would go the oxygen because that's what we know about. And on the top is going to go the CO2, which is 3 CO2. Sorry if the camera's bouncy. This table's a little bit bouncy. I just built it. it's pretty wobbly. So anyway, sorry about the camera work. Okay, so we are here to moles unknown, and we are going to finish with the molar mass of CO2. So 1 mole of CO2, and that has a molar mass of 44.009 grams. And so we'll go 10 divided by 22.4 times 3 divided by 5 times 44.009. And we get 11.8 grams. Okay, so that's an example of a liters to grams calculation. You you can also go grams to liters, and like I said, liters to liters, grams to grams. You know, it's like a choose your own adventure type of story. And I will come back with part 2 and talk about percent yield. And then I might do a part 3 with some example calculations, but we'll see how that goes. Okay, thanks, and I hope you guys are all safe and doing well. And I'll see you in part 2. Thanks.